Hello, class. This is the beginning of a lesson sequence on stoichiometry. So we're going to deal with all sorts of conversions over the next several lessons, talking about gram and mole conversions, converting between moles and particles, looking at balancing equations, limiting reactants, and even something called the empirical formula of a molecule. So first, before we can dive into our stoichiometry, we need to revisit the ideas behind atomic masses. In a previous lesson on atoms, molecules, and ions, we talked about the mass number and how that is specific to an isotope, but we need to talk about the average atomic mass, which is a weighted average based off of all of the possible isotopes for an element. We know that since each isotope has its own unique mass number, that has its own unique identity based off of that mass number. And since some of the atomic masses are more prevalent than others, we need a way to represent that when looking at a large scale sample. So our way to do that is to use the percent abundance, and which is the number of atoms of a given isotope over the total number of atoms of all isotopes of that element, and then we multiply that by 100%. When we have our percent abundances, we can multiply it by the mass of that isotope, and then subsequently add the percent abundances times the mass of other isotopes to get our average atomic mass. I'll show you this in practice. We're actually going to look at a mass spectrometry graph, and we'll be able to calculate the average atomic mass based off of the mass spec graph that we are given. One thing to note, and I've underlined it here under our definition of average atomic masses, because it's a weighted average, the average atomic mass will be closest to the isotope with the highest percent abundance. So before we jump into our calculation, just a little bit on mass spectrometers. It is a device used to measure the mass of atoms or molecules. And the way it works is by passing the atoms or molecules into a beam of high-speed electrons. We know that electrons in the atom, as a result, can be knocked off of the atom, turning them into cations. And then we apply an electric field, which causes the ions to accelerate into a magnetic field. By accelerating the ion, it produces its own magnetic field, which interacts with the applied magnetic field. Essentially, this sounds complicated, but really what it is just a giant game of the idea that opposites attract. If I'm a cation, I'll be attracted to the negative pole. If I am a cation, I'll be repelled by the positive pole. And as a result, we get some deflection. So the path of the ion as it's traveling through this tube bends in response to our magnetic field, and the degree to which it bends depends on its mass. As a result, the ions or the isotopes of your ions will separate and they'll hit a detector plate at different points, and we're able to identify unique isotopes from there. Here's a nice little picture describing exactly what we just talked about here. So you might want to pause and just take a look at that. Now, because we're using a mass spec, the way the detector works is it measures the signal intensity with which it strikes the detector. So by measuring the signal intensity, we can correlate that with the percent abundance, and then use those percent abundances to figure out the isotopic composition. So the mass spec graph shows the relative abundance, or the percent abundance, versus the mass number on the x-axis. So let's go through and do a calculation with it. Here we go. When a sample of natural copper is vaporized and injected into a mass spectrometer, the results in the figure are obtained. So it looks like we have at mass number 63, we have a relative abundance of 69.09. And at a mass number of 65, we have a relative abundance of 30.91. Now, those are percentages. Percentages we're going to have to take out of a whole. And they want us to calculate the average mass of our natural copper. Now I know on the graph it says 63 and 65, but the actual given mass values that we're going to use are 62.93 and 64.93. So we're going to take our 69.9. Actually, let me make this pen a little finer here. There we go. So we'll have our 69.09 over 100 times the mass of 62.93 AMU plus, and then we'll open our brackets again, and we'll do 30.91 over 100 times my 64.93 atomic mass units. I'm sorry, I did end up writing on the graph, but we'll just have to make that work. So, order of operations in the calculator. Oops. We're going to do 69.09 over 100 times 62.93. Sorry, I left out my multiplication sign here. 62.93. Okay. And that gives us 43.47833. And then we'll repeat the same process, but this time with my other isotope, 30.91 over 100 times 64.93. And here I get 20.069863. Now I'm going to add these two together. So 43478337. And we get an average atomic mass of 63.548. Because we were only given 4 sig figs to start with our atomic mass values, we can round that to 63.55 atomic mass units. Depending on which periodic table, you'll see most of them go to 2 decimal places, some of them go a bit further. For instance, if you're looking at P table, it does say 63.546. And that third decimal place will be slightly off, just depending on rounding and how specific the isotopes were and what sig figs they had. But the first 2 decimal places should be about the same. So 63.55 is an acceptable answer. When you're doing problems like this, I would just round to 2 decimal places just for your sanity. Okay. Go ahead and pause and you can try the next couple on your own. I will say that this last question is a little bit challenging because I don't give you any percentages. Your job is actually find the percentages. My suggestion is to set up a system of equations and then substitute and solve. Okay, on to the mole. So now that we're familiar with masses, we're going to talk about the mole, and then we're going to relate the mole to our masses very shortly. So we know a mole of something is 6.02 times 10 to the 23rd units of that substance. That is referred to as Avogadro's number. This is typically used for particles, specifically atoms, molecules, or formula units. As a result of 1 mole being equal to 6.02 times 10 to the 23rd, we actually can derive 2 different conversion factors here. 1 mole over 6.02 times 10 to the 23rd particles, or 6.02 times 10 to the 23rd particles over 1 mole. One thing I will say when it comes to the calculator here is scientific notation always throws people off in the calculator, so make sure you put parentheses around your 6.02 times 10 to the 23rd when you're putting it into your calculator. Otherwise, it's likely to get messed up. This mole map here is wonderful. We're going to take a good look at that. Um, this actually, if I can zoom out, will show us all the different ways you can convert between mass, volume, moles, and number of representative particles. So if you want to convert mass to mole, you need to use molar mass. If you want to convert moles to volume, you can only do that when you're at standard temperature and pressure. So you can use 22.4 liters equal to 1 mole. And then if you're going between moles and particles, you have to use 6.02 times 10 to the 23rd. And if you pause and just take a look at this, you can see which fraction for dimensional analysis you have to multiply by. And the reason why it changes is because we're just trying to cancel out our units. If you are in moles and you're trying to get to mass, you want moles on the bottom so that moles canceled out. If you're in mass and you're trying to get to moles, you want mass on the bottom so that mass cancels out. Pretty much the same process, and we're going to do plenty of practice with that. So let's get back here. 125 is a good size here. So we're going to do some conversions. How many molecules are in a 0.151 sample of NO? So first thing, we spent a lot of time talking about significant figures. There are 3 significant figures in our answer here. So then our final answer should also have 3 sig figs. Keep that in mind. So I've got 0.151 moles of NO, and I want to find how many molecules there are. So if I'm starting in moles, I need mole on the bottom so that it cancels, and I need my Avogadro's number on top. Now, there is no easy abbreviation for molecules, unfortunately. There is an easy abbreviation for mole. You can just leave the E off and write MOL. But for molecule, there's no easy abbreviation. So yes, you do have to write out the word molecules when setting up your dimensional analysis. Okay, so let's throw that in the calculator. 0.151 times, and then in parentheses, 6.02 times 10 to the 23rd, close parentheses, and I get 9.0902 times 10 to the 22nd. So if I do 3 significant figures here, 9.09. Now that E, if you're unfamiliar with that notation, E22 is the same as saying times 10 to the 22. So this is 9.09 times 10 to the 22 molecules. All right. Same setup for the next one, 2.51 or 2.15 moles of gold. Now, notice they're asking for atoms this time. The nice thing about Avogadro's number is it doesn't matter if you are dealing with atoms or molecules, you can use the same number. The only time it does matter is if you are given a compound or a molecule and then they ask for specific atoms of a type, because then you're going to have to use the subscripts as a mole ratio. And I can show you one of those a little later. So same deal, 2.15 times 6.02 times 10, 23rd, close parentheses. And this one also had 3 significant figures, so we are at 1.29 times 10 to the 24th, because it says E24, atoms of gold. And remember, we have to keep track of our sig figs here. So we have 3 sig figs in each of these problems. The 0 does count because it is sandwiched. Okay, and that's a decimal there. Okay, so go ahead and try this one on, oh, sorry, actually, we still got one more set to do. And then you're going to try some on your own. All right, now if we are going the other way, if we're starting in atoms and then we want to convert to moles, we just need to flip our fraction here. So same thing, still starting with 3 sig figs. So we have 8.92 times 10 to the 23rd atoms of barium, 1 mole on top because that's what we want, that's our desired unit, and then 6.02 times 10 to the 23rd atoms on the bottom. Now, again, in the calculator, you're going to need parentheses around your numbers with scientific notation. Otherwise, it could throw off how things work in the calculator. So 8.92 times 10 to the 23rd, close parentheses, times the top of your fraction, 1 divided by, and then open parentheses again for 6.02. If you do 1 over 6.02 times 10 to the 23rd, what it will do is multiply your answer by 1 over 6.02, and then it'll multiply your answer times 10 to the 23rd, which is not what we want. What we're essentially doing is dividing by 10 to the 20, or 6.02 times 10 to the 23rd. So you see I actually put 2 sets of parentheses here. Take a good look at that calculator. I opened parentheses, 1 on the top for my 1 mole, and then I opened parentheses again, 6.02 times 10 to the 23rd, close parentheses once for 6.02 times 10 to the 23rd, close parentheses again for the whole fraction of 1 over 6.02 times 10 to the 23rd. And we get an answer of 1.48 moles. 1.48 moles of barium. Now, you could also, if you're comfortable with it and you know that 1 mole is there, you could just say 8.92 times 10 to the 23rd divided by 6.02 times 10 to the 23rd, but you still need to use your parentheses. And you'll see that we get the same answer here. So we still get 1.14 or 1.48. Now, if I take out my parentheses here, watch what happens. You get 1.48 times 10 to the 46th power. So it actually treats the exponential notation differently. So you do need parentheses when you're dealing with scientific notation, or else you're going to get some incorrect answers. Okay. All right. Go ahead and, oh, no, so one more. I'm sorry. Haven't had enough coffee yet this morning. All right. So 5 point, oops, do 5.50 times 10 to the 25th molecules. Same setup as this one. Again, just because it says molecules doesn't change anything. We want 6.02 times 10 to the 23rd molecules of CO on the bottom, 1 mole on top, and again in parentheses 5.5, oops, 5.50 times 10 to the 25th divided by 6.02 times 10 to the 23rd. So notice this time I left out the 1, and that's fine. It's like I said, it works both ways as long as you have your numbers in parentheses. This is a large amount of moles. If we're looking at appropriate sig figs here, we've got 3 sig figs in our original answer, so 91.4 moles of CO is my final answer here, because 91.36 would be 4 sig figs. We round that up to 91.4. Okay, go ahead and try a few on your own. For the you try it, set 2. All right, molar masses. Let's check our time here. All right, actually I'm going to stop this video and we'll pick back up with molar masses in the next lesson.